Hi everyone, welcome back. Today's lesson is the first in a series on work and energy. And generally, when I start this unit, I ask the students to think about what energy is. And I might say, you know, what do you know about energy? And people will say things like, well, energy is something that you have when you can do things. Energy is something that you get when you sleep or when you eat. And the interesting thing about these explanations is that they actually have a lot of really important things in terms of energy in a physics sense. So there's a huge overlap between the way that we talk about energy in a casual language and the way that we're going to talk about energy in this class today. And I think a lot of people don't realize that, right? They might say, like, well, I get my energy when I eat food. And I could say, all right, so you eat meat or you eat plants. And meat, like an animal, might also eat other animals or might eat plants. And regardless, everything that gives you energy is ultimately coming from plants, which photosynthesize from the sun. So the answer to that question, where does energy come from here on Earth? It comes from the sun. And the process of energy coming from the sun and being ending up in our bodies and giving us the ability to move around and to open our eyelids in the morning and to lift a cup of coffee to our mouth, the ability to do that happens because of a whole bunch of different transformations of this energy. And so a lot of what we'll talk about in the next week is energy transformations, and how that is linked to the ability to do work, which is to move and to move objects. So let's get started. So, as always, we will start with some quick definitions. Work is the transfer of energy, and energy is the ability to do work. So, off the bat, you can see that there's clearly a very close knit relationship between work and energy, which we are going to explore today. Let's start with work. Work is said to be done on an object when there is a force, and that force causes the displacement of the object. Now, I'm going to refer often to our definition of work when that word work comes up. So I could say this sentence like this: energy is transferred to an object when a force causes a displacement of the object, right? That is also true if work is the transfer of energy. So work, the equation for work is that work, which is represented as this W, is equal to force multiplied by displacement. Now, if you are to, let's say, push on a chair and that chair moves across the floor, well, you've done work to the chair. Now, the energy transfer to that chair floor system happened because of the component of your force that was parallel to the floor. Let's say, for instance, that you were pushing completely horizontally. You're going to push that chair across the floor in a much more efficient manner, right? A lot more of your energy is going to be transferred into the system when you push parallel to the floor. It's easier. I guess depending on other variables, it might not necessarily be easier for you to push at that position, but there's definitely a more efficient energy transfer than, let's say, you're pushing down at some angle, right? If you're pushing a chair across the floor and you're pushing at, let's say, I don't know, a 60-degree angle to the horizontal, it's only the component of your force that's parallel to the floor that's actually contributing to the motion of that object. So the work equation can be more generally written as this: work is equal to some applied force times the displacement multiplied by the cosine of angle theta, where that angle theta is the angle between the force and the displacement. Now, the SI units for work is the joule, which, as you can probably imagine from the equation above, is mathematically equivalent to a Newton meter. So let's try this problem. A banana has 3 times 10 to the 5th joules of energy stored within it. How many kilocalories is this? And I gave you below the conversion between calorie and joules. Pause here, give this a try. So this problem is really a conversion problem. I'm going to start with my value 3 times 10 to the 5th joules and put that over 1. You'll notice here that I'm going to use the factor label method of unit conversion. I'm going to get out of joules into calories and then out of calories into kilocalories. So my first conversion will give me out of joules into calories. And I'm given that 1 calorie is equal to 4.184 joules. Now, if I were to multiply this out, I'd end up in calories, but I really want to be into kilocalories. So I need to think about my metric prefix kilo, which is associated with 10 to the power of 3, and that goes next to my base unit. So I have 1 kilocalorie equals 10 to the 3rd calories, and now, joules cancel, calories cancel, I end up in kilocalories. So what I'll do here is I'll take 3 times 10 to the 5th, and I'll divide that by 4.184 times 10 to the 3rd, which gives me 71.7 kilocalories. Oops, 71.7 kilocalories, which seems reasonable. That is, to my understanding, that is about what a banana is about 100 kilocalories. And by the way, you probably know this from chemistry, but we actually use the word calories to represent kilocalories when we talk about food. That's what I mean. So like, I don't know, I have a Pocky here. Not to get off topic, but on nutritional values, it says based on 2,000 calorie a day diet. That actually means 2,000 kilocalories. So there's like a weird discrepancy between language here and the actual language in science. And if you took chemistry, you more than likely know this already. But anywho, nice work. All right, so let's consider a couple examples. Let's say I apply a horizontal force to a car to move it 10 feet. Is work done? Now let's say a student holds a heavy chair at arm's length for several minutes. Is work done? Well, for my first example, work is done because there's a force that was applied and that force caused the object to become displaced. In the second case, there was no work being done. Now, it might have been challenging to hold that heavy chair, especially if it was, really heavy. And you're definitely exerting a force onto the chair, but the force that you're applying isn't causing any motion, which means you're not transferring any energy into the system here. So your muscles are working hard, right? There's internal biological work and energy inside of your body, but that energy is going into maintaining muscle tension, not in changing the chair's kinetic or potential energy, which is what's required for work to have been done. So in the second case here, holding a heavy chair arm's length, you do not do work on the chair in this case because there was no displacement. Let's note that work here is a scalar, which might seem funny for you to think about, okay, you multiply 2 vectors together and you get a scalar, but that is certainly a possibility. You could multiply 2 vectors together and get a scalar. The sense work is a scalar. The sign of work, so whether it's negative or positive, does not indicate the direction of work, but rather indicates if the system has lost or gained energy. So think for a second about the nature of this relationship here between force and displacement. Let's say you have an object moving to the left, so it has a negative delta x, or in our traditional reference frame, right? We say negative is, or left is negative. So we have a negative displacement. Now let's say there's friction. That friction will be pointed right? It opposes motion. So if friction is pointed right and the displacement is left, then you're going to get a negative sign for work. And that negative sign doesn't mean that work was done to the left. It means that the system lost energy. And as we'll find out in the next lesson, that wasn't the energy wasn't lost in the universe. It was just transferred into a different type of energy. But the important thing here being that a negative work indicates that the system lost energy. That energy was transferred into some non-mechanical form. All right, let's try our second problem here. A 30 kilogram box is pulled with a force of 100 newtons applied at an angle of 30 degrees to the horizontal. The box moves 5 meters. There is a 50 Newton force of friction. So that is here leftward force. I want you to just tell me the work done by friction. I want you to tell me the work done by the force tension, and then the net work done. And net work would be the total work. So find the work done by every force and add them up. All right, so for this one, I'll actually draw a free body diagram. I find that helpful. So let's see. I have my normal force. I have my force tension. I have the X component of tension here and the Y component of tension here. I have my force gravity or my weight force, and then I have the force friction over here. Now I'm told that the mass of this box is 30 kilograms. That the it says applied force, but I called it tension on my diagram, which is fine. So that's 100 newtons. That my angle theta here is 30 degrees, and that the displacement of the box is 5 meters. And since friction's pointed left, I'm assuming my displacement's 5 meters to the right. And then I'm also told that I have 50 newtons of force opposing the motion, so it's negative 50 newtons of force. My first question says, what is the work done by friction? So the work done by friction is going to be equal to the force of friction times my displacement. Now, friction is always going to be parallel to the displacement. So, the work done by force is, it's really the component of the force that's parallel to the displacement. But since my displacement is to the right, that's my delta x, and friction's parallel to that. So I'm using my entire value for friction here. So negative 50 multiplied by 5 gives me negative 250 joules. So 250 joules of energy was lost from the system due to friction. B says, what is the work done by the force tension? So the work done by tension is going to be equal to the component of tension that's parallel to the displacement. So the X component of tension multiplied by my displacement. Right now, there's 100 newtons of tension, but it's only this component that's contributing to the energy transfer. So I would take force tension times my displacement and then multiply that by the cosine of angle theta, right? Because Ft cosine theta is Ftx. So 100 times 5 times the cosine of 30. $433 joules of energy was gained by the system due to tension. Part C says, what is the net work? That is the total work. So the net work I can find in two ways. I can find the net force and multiply it by the displacement, or I can add up the work done by every force. So the work done by tension plus the work done by friction plus the work done by gravity plus the work done by normal. And I'm going to use the second method. It's going to be easier for me since I already have two of these forces. So the work done by tension is 433 joules, plus the work done by friction is negative 250, plus the work done by gravity is 0 because there is no component of gravity that is parallel to the displacement. So yes, gravity is present. Yes, gravity is acting on this object, but it is not contributing to the energy transfer, right? There's no component of my force gravity that is parallel to this. So plus 0. And then the work done by normal is also 0 for the same reason, right? The normal force is perpendicular to the displacement. The component of the normal force that's parallel to delta x is 0. So I'm adding 0. So I have 433 minus 250 plus 0 plus 0 gives me 183 joules of energy. So as my net work. So the next piece to today's lesson is going to be talking about energy. And if I show you guys these 4 images and ask you, hey, what type of energy do all these things have in common? You might say, well, they're all moving. And if you remember from perhaps you took physical science or introductory physics or even chemistry, you have most likely talked about kinetic energy, which is the energy associated with an object in motion. Now, kinetic energy, which is represented as the symbol Ke, is equal to 1/2 mv squared. So kinetic energy is a scalar, which is why you do not see that arrow above this variable Ke. And it is determined by the mass and the speed of the object. Mass and speed also being scalar quantities. The SI unit for kinetic energy is also the joule. So you can see from this equation that a joule is also mathematically equivalent to a kilogram meter squared per second squared. But it's easier to say joule. So kinetic energy depends on mass and it depends on the speed of the object squared. You can see here, hopefully from this relationship, that an increase in the speed changes the kinetic energy by a factor of that speed squared, right? So if you double the speed that an object's moving at, the kinetic energy multiplies by a factor of 4 because v is squared. This is why automobile accidents can become really, really serious with minor increases in speed. There's a lot more energy associated with a car moving at 40 miles per hour than a car moving at 20 miles per hour. In fact, there's 4 times as much kinetic energy associated with a car moving at 40 miles per hour compared to one moving at 20 miles per hour. So this speed squared relationship is something we'll talk about a bit in this unit. All right, let's try these 2 problems. A car with a mass of 7 times 10 to the 5th grams is moving with a speed of 20 meters per second. Calculate the kinetic energy of the car. Then, when you're done with that, a tennis ball is traveling at 21 meters per second and has a kinetic energy of 55 joules. Calculate the mass of the tennis ball. So these are 2 independent problems. I'd like you to pause the screen and try them now. All right, let's list out my knowns. My mass is 7 times 10 to the 5th grams. My speed is 20 meters per second. Now, kinetic energy, which is what I'm looking for, is equal to 1/2 mv squared. So kinetic energy depends on both mass and speed, which is great because I have a mass, I have a speed. But I hope you notice that that mass is not in the proper SI unit, which means if I use grams in this equation, I'm not going to end up in joules. But I want to end up in joules. So I'm going to convert from grams to kilograms. So what I can do here is I can take 7 times 10 to the 5th grams, put it over 1, and convert it into kilograms. Kilo is associated with 10 to the power 3, or 1,000. So I put that next to my base unit, and I get 7 times 10 to the 5th divided by 10 to the 3rd gives me 7 times 10 to the 2nd, which is 700 kilograms. That's the mass I should use. So now plugging in 1/2 times 700 times 20 squared. So 20 squared is 400. Half of that is 200. So 1400 or 1.4 times 10 to the 1, 2, 3 third joules. That would be my answer. All right, second part. we have a tennis ball traveling at 21 meters per second. So our speed is 21 meters per second. Has a kinetic energy of 55 joules. And I want to calculate the mass. Now, this is a good problem to do because I know the mass of a tennis ball more or less. Like, at least I know the magnitude of it, right? A tennis ball is going to be like, you know, 1 kilogram. It's not going to be like a 100th of a kilogram, and it's not going to be like 100 kilograms. So I should have a good sense of what, if I get the right answer, not just knowing that, tennis ball is probably, less than half a kilogram. A kilogram, by the way, is 2.2 pounds. So I guess a tennis ball is maybe like half a pound. I don't know. So maybe a quarter of a kilogram. Anywho, these are my SI units, so that's good. So one kinetic energy is 1/2 mv squared. If I want to isolate m, I can do that by getting rid of that coefficient 1/2, which means multiplying everything by 2. And now dividing by v squared. So I have m equals 2ke divided by v squared, which would be 2 times 55 divided by 21 squared. So 110 divided by 21 times 21 is 0.25. So 0.25, kilograms would be my answer, which again, it falls within the right order of magnitude. All right, so that brings us to the work kinetic energy theorem. Now, generally when I introduce this, I like to derive the work kinetic energy theorem. And you know what? I should derive that. So why don't you give me a moment and I will show you where that theorem comes from. All right, so to derive the work kinetic energy theorem, what I want to start with is our definition of network, which is that the network is equal to the net force acting on an object multiplied by the displacement. And next, what I can do here is substitute in Newton's second law for net force. So I have the net work equals mass times acceleration times delta x. And what I'd like to do is I'd like to write out the work in terms of, you saw eventually I'm going to get to kinetic energy, which is 1/2 mv squared. So what I really would like to do is I'd like to somehow cancel out the displacement. And also have, instead of this being written in terms of acceleration, I like to be written in terms of velocity. So I want to use the equation that relates initial, final velocities to displacement because I want to cancel it out, to acceleration because I want to substitute in for A. So the kinematics equation that has V final, V initial, acceleration, and displacement is this one right here. V final squared equals V initial squared plus 2A delta x. And what I'd like to do is I'd like to isolate A and then substitute in that expression for A right here. So first thing, to get A alone, I'm going to subtract V initial squared from both sides. And I get V final squared minus V initial squared equals 2A delta x. And now I want to divide by 2 and divide by delta x. So I get V final squared minus V initial squared over 2 delta x equals A. So this expression here is mathematically equivalent to A. So I will go ahead and substitute it in for this A right here. And I get the net work is equal to mass times V final squared minus V initial squared divided by 2 delta x multiplied by delta x. Now, this is great. My displacements cancel, right? Because delta x divided by delta x is 1. And I'm also going to pull out this term 1/2. So I'm going to clean it up a little. So my net work is equal to 1/2 times m times v final squared minus v initial squared. And you see that I'm very focused on my vector notation, which is mostly habit, but I hope you realize that squaring
a negative sign gives you a positive sign anyways. So when you square a vector here, this velocity vector, you end up with a scalar. So I really don't need to use those arrows above my variables anymore. I'm really talking about speed here. And let me distribute my coefficient 1/2 m. I get net work equals 1/2 mv final squared minus 1/2 mv initial squared. And I hope you can see at this point now that this is, I'm pretty much done, right? In terms of deriving the work kinetic energy theorem, which is that, 1/2 mv final squared is the final kinetic energy, and 1/2 mv initial squared is the initial kinetic energy. So here you can see that the net work is equal to the change in kinetic energy.
Great. Okay, so now you have a better understanding of what I mean when I say the net work is equal to the change in kinetic energy, right? And I guess I want to note here that we're really talking about the net work, the total work. And as you saw from that derivation, that comes from the net force equation, Newton's second law. So, this relationship here between work and energy, it is it it really feels a lot like this first slide about work and energy, right? They're very closely related. Work is the transfer of energy, and energy is the ability to do work, which is why they're both also measured in joules, right? They are mathematically equivalent, the net work and the change in kinetic energy. Okay, our next problem. A box of 17 kilograms starts at rest and is pulled by an applied force parallel to the ground. After being pulled a distance of 3.3 meters, the velocity of the box is 1.7 meters per second. How much energy did the system gain? Go ahead and pause it. Try this now.
This problem we should definitely draw a free body diagram and list our unknowns. So a box of 17 kilograms starts at rest and is pulled by an applied force parallel to the ground. I don't know what that value is. After being pulled a distance, delta x, of 3.3 meters, the velocity of the box is 1.7 meters per second. We want to find out how much energy the system gained. Now we know that that's also the work done on the system. So we can solve this a couple ways. I said I draw free body diagrams. Let me do that. I have my applied force. There's no reason that I should think that this is a frictionless system, so I have friction. I have force gravity, and I have a normal force pulling up on it. Okay, so let's see. We have the net work is equal to the change in kinetic energy. Now, net work is net force times displacement. Do I have the ability to find the net force? Do I have mass and acceleration? Well, I have 1, 2, 3 kinematics quantities, so I can definitely find the acceleration if I wanted to. So the first way I can solve this problem, which is how some of you may have done it, is to find the net work, which is equal to the net force times the displacement. Now, net force is the mass times the acceleration, so the net work is equal to the mass times the acceleration times delta x. Now, this value I need to find using kinematics. So the equation that relates v initial, delta x, v final to acceleration, if you look at your list of kinematics equations, you're going to use the one without time, which is this one. V final squared equals v initial squared plus 2a delta x. Now, you'll probably notice that this is also the equation we use to derive the work kinetic energy theorem. So there's obviously a reason for that. Now, if I were to isolate a from this, I would say that acceleration is equal to, we'll subtract vi squared and divide by 2 delta x. So I get v final was 1.7 squared minus 0 squared divided by 2 times 3.3. And that gives me an acceleration of 1.7 times 1.7. Divide that by 6.6. Gives me 0.44 meters per second squared. And now we can plug that in to find our network. Our network is equal to our mass, right, which is 17, times acceleration, which is 0.44, times displacement, which is 3.3. So that times 17 times 3.3 gives me 24.5 or 25 joules. That is my amount of energy that the system gained. Let's try this a different way. Let's find the change in kinetic energy. Change in kinetic energy is equal to KE final minus KE initial. So let's first find the final kinetic energy. That would be 1/2 mv final squared. So 1/2 times 17 times 1.7 squared is 24.5. Oh, wow, look at that. Which you probably expected because, again, this was derived. The work kinetic energy theorem was derived from this relationship. So, anywho, I have 25 joules as my final kinetic energy. My initial kinetic energy is going to be equal to 1/2 mv initial squared, which would be 1/2 times 17 times 0 squared, which would be 0 joules, which means that my change in kinetic energy is KE final minus KE initial, or 25 minus 0 equals 25 joules. So my answers agree. You probably did one of these, I'm sure.
All right, let's talk about potential energy. This is energy that's associated with an object's position. And I'm sure you are looking at this picture of Humpty Dumpty. Maybe you're putting it together why I have a picture of him here. But I think it's useful to think about the relationship between potential energy and kinetic energy when we think about a situation where an object's falling towards Earth, right? So Humpty Dumpty's sitting on the wall and, he falls off it. And as he is moving down towards the surface of Earth, you guys know that he's accelerating because there's a gravitational field. So he's speeding up. And that might beg the question of where's that kinetic energy coming from, right? If he's speeding up as he's moving towards Earth, where is that energy coming from? It's not just appearing in this system. It's being transferred from the fact that he was high above the Earth, right? He was at some height above the surface of the Earth, and stored within him was some amount of energy due to that height. And we call that potential energy. And specifically, when you have energy associated with your position and your position's above a gravitational or within a gravitational field, we call it gravitational potential energy. But there's also elastic potential energy, which is another type of energy that's associated with an object's position, but this is something being stretched or compressed. So take, for example, an archer. The archer takes an arrow and they stick it in the bow and they stretch that bow back, or the string of that bow rather, until there's all this stored energy in the arrow, and they release it, right? And the string of the bow snaps back into place, and while it's doing that, it pushes the arrow into the air, and the arrow starts to move. And that kinetic energy came from that stored potential energy, which we call elastic potential energy. So the wrecking ball over here has gravitational potential energy stored within it because it's in a gravitational field. And this arrow here has stored within an elastic potential energy. So gravitational potential energy is given by the equation mgh, where m is mass, g is acceleration due to gravity. On Earth, that value is 9.81 meters per second squared. And h is the height above some equilibrium position or some reference position. Now, before I elaborate on what m, g, and h mean a little bit more, I'd like us to see real quick that potential energy is a scalar here, right? There's no vector notation above it indicating that it does not have direction, And that's the same is true for m, g, and h, right? Mass, acceleration due to gravity, and the height. They're all scalar quantities, so you don't have a direction with either any of those values. Now, mass is measured in kilograms. Acceleration due to gravity is in meters per second squared. And when you use this equation here to solve for the gravitational potential energy of an object on Earth, you would use 9.81, not negative 9.81, because negative 9.81 is a vector. That is the y component of the acceleration for an object in free fall, for example. But here we're looking at scalars. And so when I want you to use negative 9.81, I put an arrow over that g. But when I'm talking about the scalar form, it's just 9.81. All right, so we have a person on a swing. At which of these positions is the gravitational potential energy the greatest? Hopefully you would say, well, position A, and then C, and then B. Because gravitational potential energy depends on the mass, which isn't changing for this boy, the acceleration due to gravity, which isn't changing because he's not changing his, location. He's on Earth this whole time. And the h is the height, so that is changing, right? Position A is the largest height, so it's going to be the largest potential energy here compared to C and then B. Now, that h height is the height above some zero location, and we pick that zero location. So if I'm looking at this system, I might pick the zero location as the ground. A lot of times people use that as the reference point, like the ground. Or, sometimes if it is a pendulum or a pendulum system like this, they'll use this bottom position as the zero location. And so in that case, the height would just be, the vertical difference between this spot right here and this spot right here. But regardless, you're really focused on the change in energy often. And the change in energy is going to be the same regardless of the reference point. But just notice that h really means the height above some reference point. All right. A 15 kilogram mass is suspended 10 meters above Earth. What is the gravitational potential energy stored within that mass? An object is resting on top of a hill that is 40 meters tall. Stored within it is 8 times 10 to the 4th joules of energy. What is that object's mass? Go ahead, pause the screen, and try these.
All right, so let's start with our knowns. A 15 kilogram mass is suspended at a height of 10 meters. I'm going to use the ground as the zero position. And we want to find the gravitational potential energy. That's equal to mgh. So kilograms is correct for my SI unit for mass, and height would be in meters. So m is 15. G is 9.81 meters per second squared. You can use 10, right? I'm going to use 10 because this is only one sig fig anyway. So m was 15, g is 10, and then our h is 10. So we have 1,500 joules. The second part says an object is resting on top of a hill that is 40 meters tall. Stored within it is 8 times 10 to the 4th joules of potential energy. What is the object's mass? Now, the equation that relates these things together, along with our acceleration due to gravity, would be the gravitational potential energy equation, right? Which makes sense because this is stored above gravitational field, so this is the equation we would use. So if I want to solve for m, I'm going to divide both sides by gh, and I get m equals pe over gh. So I have 8 times 10 to the 4th divided by 10 times 40, which is going to be 8. Let's see, 8, 1, 2, 3, 4. 1, 2, 3, 4. Divided by 400. So let's get rid of those zeros. 800 over 4 is going to be 200 kilograms as our mass.
And that brings us to our second type of potential energy, which is elastic potential energy. This is associated with an object being stretched or compressed. And we can see that the equation for elastic potential energy actually looks a bit like the equation for kinetic energy, right? We see that coefficient 1/2, and then we see that variable squared here. So elastic potential energy is equal to 1/2 kx squared. Now, x is our distance from some equilibrium position, so a resting location, and k is the spring constant. That is a value that's measured in newtons per meter, and it tells you how stiff a spring is. So, I don't know, let's say I have maybe, let's say, a person is jumping up and down on a trampoline. Well, there's some spring constant associated with the trampoline, right? Because trampolines stretch when you stand on them, and so they they have some, if you're standing on a trampoline, there's some x value, right? The vertical displacement, for instance, the magnitude of that would be the distance here. And to find the potential energy associated with an object on a trampoline, you would need to know the spring constant of the trampoline and the amount that the trampoline was stretched in the vertical direction. Elastic potential energy is also measured in joules. So we've seen today that everything we've looked at so far is measured in joules. That's energy, so potential energy, elastic gravitational potential energy, elastic potential energy, and gravitational potential energy, as well as kinetic energy, are all measured in joules. All right. A spring with a spring constant of 98 newtons per meter is stretched 1.9 meters. What is the potential energy stored in the spring? How far does a spring need to be compressed to have 1,540 joules of energy stored within it? And I gave you that spring constant K, 13.5 newtons per meter.
All right, our knowns are a spring constant, that's K, of 98 newtons per meter, right? Spring constant, that tells you how stiff the spring is. So, what this means is that if I applied 98 newtons of force onto this spring, I would stretch or compress it 1 meter, right? That's the amount of force required to move it 1 meter. And it is stretched 1.9 meters. And we want to find the potential energy. And this is, of course, elastic potential energy. So the elastic potential energy equation is 1/2 kx squared. And I'm looking for this value, which is already isolated. So 1/2 times 98 times 1.9 squared. That would be 0.5 times 98 times 1.9 times 1.9 gives me 177 or 180 joules stored within it. Now our second question here, we want to find how far does the spring need to be compressed. So we're looking for x, and our k value, our spring constant, is 13.5 newtons per meter. And we're told that there is 1,540 joules of potential energy stored within it. So PE equals 1/2 kx squared, and I want to isolate x. So first thing, let me multiply everything by 2 to get rid of that coefficient 1/2. So we have 2 PE equals kx squared. Now let me divide everything by k to get rid of that coefficient k. So I have 2 PE over k equals x squared. And lastly, to undo the squared, I'm going to take the square root of everything. So the square root of 2 PE over k equals x. And now I can go ahead and plug in. So x equals the square root of 2 times 1,540 divided by 13.5. So let's see, 1,540 times 2 divided by 13.5, and I'll take the square root of that answer, and I get 15 meters.
All right, so this is our last problem today, which is I want you guys to state the types of energy that are present for each of the situations described below. So here, at the very peak of the trajectory, the person is momentarily at rest while they have jumped to their full height. Now, this situation here, the person is coming back down towards the trampoline. They haven't touched the trampoline yet. And the very last situation, the person's at the bottom of the jump where they have fully stretched the trampoline downward and are momentarily at rest. So I'd like you guys to tell me the types of energy that are present at each of these. All right, at the top of the jump, the energy of the system, so the trampoline person system, is gravitational potential energy. There's no kinetic energy because they're at rest, and there's no elastic potential energy because nothing's being stretched or compressed. So at the top of the jump, it's only gravitational potential energy. Midway through the jump, there is gravitational potential energy because they're still moving down towards their resting position. So there's still some height, and they are moving. So there's kinetic energy as well. At the very bottom of the jump, it is all elastic potential energy stored within this system. So now the energy has been transferred into elastic energy as the trampoline stretches downward. And since they're at the bottom of the jump, they are momentarily at rest. So there's no kinetic energy at that point. So as a summary, we have gravitational potential and kinetic, elastic potential. Thank you guys so much for being here today, and I will see you soon.